All right, this is a video on linear programming, and we'll start off with an introduction and then do one solved example. So linear programming is a great tool to use, particularly in the scenario of maybe working in a small business and you have to decide how many of a couple different options you might, or a couple different products you might need to create. And so we'll look at that in an example today. But we're going to be using a system of linear inequalities to graph the constraints of a real-world situation. All real-world scenarios have real-world constraints. What are our limitations? And then we'll test the vertices of that feasible region, is what we call it, to see which gives us the best outcome. So our steps are to certainly read the problem for understanding first. Okay, make sure you really understand what's going on. And then we have to identify what is a constraint and what is an objective function. An objective function usually refers to money and usually refers to something we're trying to optimize or maximize. The constraints are our limitations in the scenario. We're going to take those constraints and graph them as a system of linear equations, and that gives us the feasible region. And you see a picture of that in the graph right here. It looks like we have three different constraints, a red, green, and orange line that all narrow in or restrict what our choices might be, and that gives us the feasible region. Okay, and then what we're going to do after that is determine the vertices of the feasible region, which I will be circling on this graph down here. So this feasible region here seems to have 5 total vertices, and we will then test the coordinates of each vertex in the objective function, and usually in our money function, and which vertex gives us the best possible outcome. Okay. The real thing to keep in mind is one of the great things about linear programming is your best possible outcome will always happen at one of the vertices. Okay, so we'll look through that in an example as well, but you need to remember that your best possible outcome will always occur at one of the vertices of your feasible region, one of the corners of your feasible region. All right, so let's look at this scenario. You're screen printing sweatshirts to sell at a local festival. Okay, you have 20 hours to spend on the shirts, and you have a budget of $600 to spend on supplies. So those seem like limitations. So those are going to be our constraints. We have limited time and we have limited money. And we want to make at least 50 items to sell. So that's another constraint based on our business goal. We want to sell at least 50 items. Additionally, t-shirts take 10 minutes to make, cost $4 in supplies, and sell for a profit of $6. And then some more information for sweatshirts. What I'm going to highlight in yellow here are the pieces that go into our objective function. So we're not going to worry about those quite yet. We need to worry about the constraints first. So we're going to try to maximize profit, but we'll save that for the end. Okay, so let's think about what our constraints might be, what our limitations might be. So first off, we can say, let's let X equal number of t-shirts. So it's really helpful to define your variable, and Y is number of sweatshirts. Okay, so make sure you're clear on what your X and Y variables are. All right, so we can write some constraint equations next. And one constraint seems to be limited to time. Okay, we only have 20 hours to spend. So we can say that each t-shirt takes 10 minutes to spend, and 10 minutes to make, and each sweatshirt, I believe, takes 30 minutes to make, and that needs to be less than or equal to not 20, but 1200. So we're working consistently in the units of minutes. So we took the 20 hours and multiplied by 60 to get 1200. Another constraint that we have is just our goal, or we have a business model, we have a goal in mind where we want to be able to sell at least 50 items. Okay, so we want to create at least 50 items, produce at least 50 items. And lastly is our costs, where we only have $600 available, so something is going to be less than or equal to 600. And it looks like t-shirts cost $4 each and sweatshirts cost $20 each, just in supplies. Okay, and then we always have some real-world constraints as well. X has to be greater than or equal to 0, and so does Y. Okay, we can't create or produce negative t-shirts or sweatshirts. What we're going to do is graph that up on a graph. First, what I'm going to do though is let's simplify our graph, or simplify some of our inequalities. We can divide top and bottom there by 10, or excuse me, divide left and right sides there by 10, and we get x plus 3y is less than or equal to 120. And we can do the same thing with this constraint as well. Divide left and right by 4, and we get x plus 5y is less than or equal to 150. That's going to really simplify things. Okay, so let's put all our constraints together, and I will copy them down to our graph down below. And let's go ahead and copy those. So that's our final set of constraints, and we'll go ahead and make a graph down here. Okay. All right, so our first one is, well, let's also just keep in mind x and y are greater than 0. That's our real world constraint. That's why I'm only giving us the first quadrant here. I'm not allowing us an option of plotting any negative values for x and y. So you can think of these two constraints as kind of being checked off already. Okay, let's look at the first one. X plus 3y is less than or equal to 120. I want to do some color coordinating here. We will have a green, we will have a purple, and we will have a blue constraint. Okay, so first let's work with our green one, and I will just plot the boundary line first. So x plus 3y is equal to 120. So if y is 0, x will be 120. So that's a point right there. And if x is 0, y will be 40. So that's a point right there. Okay, and so I can go ahead and plot that boundary line. These are all solid boundary lines. That looks pretty good right there. Okay, so we have this one plotted up. Let's do our purple one. X plus y is greater than or equal to 50. We'll do some shading down the road, but let's plot the boundary line first, which is x plus y is equal to 50. Okay, so that's a pretty easy one to plot. We just have two y-intercepts at 50, or two intercepts at 50 on the y-axis and 50 on the x-axis as well. Let's go ahead and plot that one. Looks like right there. And then lastly, so we got that guy. Let's do our blue one. X plus 5y is less than or equal to 150, so the boundary line is x plus 5y is equal to 150. Let me actually bring all these down so we have some easier things to work with there. Okay, so x plus 5y is equal to 150. We'll do that in blue. So if y is 0, x is 150. And if x is 0, y is 30. Okay, so we have this boundary line right here. I think you can see that it's going to be important to actually shade things pretty carefully and graph things pretty carefully and neatly. Okay, so it looks like we got all of that done. Let's do some shading now, and we will shade below on green. And I might erase some of my shading away once I figure out what my common area is. We're shading above on purple. And we are shading below on blue. Okay, so what zone is our common shaded zone? It looks like it's this zone right in here. Okay, that zone fits all the criteria that we need to work with. So let me clean up things a little bit here. And I think we can see now that we're working with this. This is our common shaded zone right in there. Okay, so we have some corners, some vertices of this, which I will be circling in black right here. Okay, so it looks like we have one that's 25, 25. Okay, 25 of each product. We have one right here that is 75, 15, it looks like. We have one here that is 120, 0, and one here that is 50, 0. Okay, so all of those points meet our constraints. we have enough time to make them, we have enough money to produce them, and they meet our goal of making at least 50 items. So now we have to think about our objective function. So going back above, I think you can see that our objective function will be a profit of $6. Profit is equal to $6 for each t-shirt plus $20 for each sweatshirt. Okay, so that's our objective function. I'm going to copy that and bring it down. And so this is what we need to test each point in and see if which gives us the most money. I hope you can see that this point that I'm going to highlight in yellow down here, we don't need to test. Okay, it should be clear that this other point in yellow, the 120, is going to give us a higher profit than just selling 50. Okay, so selling 120 t-shirts will certainly give us a greater profit than selling only 50 t-shirts. So I am simply just not going to test that, save a little bit of time. Okay, so we're going to test each point. So we're going to test the 120, 0, we're going to test the 75, 15, and we're going to test the 25, 25. Let's just see which gives us the greatest profit. So let's see here. So this gives us a profit of 6 times 120 plus 20 times 0. This gives us a profit of 6 times 75 plus 20 times 15. And this one gives us a profit of 6 times 25 plus 20 times 25. And we're simply going to see which one of those combinations makes us the most money, and that'll be our solution. All right, 6 times 120 is $720. Okay, so that would be our profit if we made 120 t-shirts and 0 sweatshirts. 6 times 75 plus 20 times 15, that gives us, let me see here, $750, so a little bit more of a profit. And then 6 times 25 plus 20 times 25 is $650. All right, so we get our highest profit is $750. So that means our choices will be to make 75 t-shirts and then additionally 15 sweatshirts. That is the combination of sweatshirts and t-shirts to make that fits all of our constraints in terms of time and money and our business goal of making at least 50 items, and then yields the maximum profit. All right, that's a good one. We got through it. That's a good place to stop.